Today we'll be looking at chapter 1.6, which is classifying polygons. So our essential question here is just how can angles and sides be used to classify shapes? And hopefully by the end of this section, you will be able to describe polygons based on their angles and sides. All right, so first of all, what is a polygon? In geometry, a figure that lies in a plane is called a plane figure. And a polygon is a closed plane figure with the following properties. So first, it has at least 3 sides. And sort of more specifically with that 3 sides, no curves. So a circle is not considered a polygon. It's closed. So what that means is there's no like openings, like this would be a non-closed shape that doesn't close all the way. And then we have no overlapping sides. And more specifically for that, each vertex is connected to 2 sides. So this is true for all polygons, that a vertex has to have 2 sides. And what the heck is a vertex? Well, each end point of a side is a vertex of the polygon. And the plural of vertex is vertices. So when we name a polygon can be named by listing the vertices in consecutive order, meaning in order as you follow them. So for example, if we went A, B, C, D, E, that would be a polygon. Another way of naming this polygon would be C, D, E, A, B, and so on. Continuing these definitions, we also say that a polygon is convex if no line that contains a side of the polygon contains a point in the interior of the polygon, so it doesn't point in. It might be more clear to understand what convex is when you understand what concave is. So a polygon that is not convex is called concave. And I think of it as caving in. There's a point where you can almost push and it went in. So that's considered the interior, and that's concave. So if you don't have that, then the polygon is considered convex. So example 1 just wants us to tell whether each figure is a polygon and whether it's convex or concave if it is a polygon. So we kind of have those 3 checks that we want to go through, and this one is closed, and it does have at least 3 sides, but it has this overlapping side here, so we can see that these 2 vertices have more than 2 sides. So we'd say not a polygon because it has an overlapping side. Or more specifically, it has those 2 vertices that have 3 sides connected to them. This next one is closed, more than 3 sides. And no overlapping sides. So this is a polygon. And more specifically, this is a convex polygon. Part C, we have a curved side here, so this is not a polygon. And for part D, we have this is closed, more than 3 sides, no overlapping sides. But if you notice here, we have that caving in part, so we consider this a concave polygon. All right, so we can classify these polygons as concave or convex, but we can also describe them based on their number of sides. So you'll know a couple of these. Number of sides, the type of polygon, if it has 3 sides, it's a triangle. 4 sides is a quadrilateral. You can think a quad has 4 wheels. Quadrilateral. 5 sides is a pentagon. Think of the Pentagon in Washington, D.C., 5 branches of the military. 6 is a hexagon. 7 is a heptagon. 8 is an octagon, think octopus. 9, this is my favorite, I just like saying it. 9 is a nonagon. Nonagon. 10, you can think of a decade, so this would be a decagon. Oops. I don't know why the book skips 11, but that's fine. And 12 is a dodecagon. So if you know Spanish, you can think dos decagon, 2 decagons, 2 plus a decagon. And then we also have, when you have the number of sides as n, this is a more general case, we'd call this an n-gon. And so the term n-gon is used where n is the number of sides. So you can also use this, so if you had like a 14-sided polygon, there is a fancy name for it, but you could always just call it a 14-gon. All right, so we can classify them by the number of sides. We can also classify them by their angles and their side lengths. So we say a polygon is equilateral if all sides are equal. And we would denote that here by putting these lines through it. That indicates that all of the sides are equal. Then we have equiangular, where all angles are equal. And I should say all interior angles, just to be more specific, because we're not talking about those outside angles. Oops. And we would denote that with an arc, and more specifically here, these are all right angles, because this is a rectangle. So we would denote that way. And then finally, we say that a polygon is regular if all sides and all angles are equal. So specifically, a regular polygon is equilateral and equiangular. Sorry to run out of room here. So this would be denoted with these lines, saying all sides, and then all angles are equal here. All right, so example 2 is just classifying polygons. So the first thing I like to do is name my, so these are all polygons, and I want to name the number of sides. So you can say n, and this is just number of sides. So for this first one, we have 1, 2, 3, 4, 5, 6 sides. Then we also have all these markings that show that this has equal angles and equal side lengths. So we would say that this is so if it's equilateral and equiangular, then instead of a then, I'm going to put this fancy symbol. That means then it's regular. So when we name it, you would either put the equilateral, equiangular, or regular before the name of the polygon. So since it's regular, I would call this a regular hexagon from the number of sides. Part B, here my n is equal to 4. This is not equilateral because notice these 2 sides are equal, but then these 2 sides have the double thing. So that means that the 2 top sides are equal to each other, and then separately the 2 sides are equal to each other. And then same thing with the angles. You have 1 arc versus 2 arcs. So this is not equiangular, it's not equilateral, so therefore it's not regular either. So this is just a quadrilateral. We could say it's a convex quadrilateral, but it didn't ask for that here. And then finally, this last one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. And then it looks like this is equilateral and equiangular. We have all these one lines, right? So it's definitely equilateral. But if you look at the angles, we have to be a little careful here because we want to count interior angles. And that is not equal to 90 degrees, right? That'd be 270 degrees. So this is not equiangular, it's just equilateral. So we would say that this is an equilateral dodecagon. So that's naming these polygons in a nutshell. It's pretty straightforward. We'll have more. I'm going to continue with these notes tomorrow with you in class. But if you have any questions, let me know, and you can get started on your chapter 1.6 practice 1.